Hello, folks. How's everybody doing? I hope you're doing fine, just like me. I've recovered quite a bit. I think I'll survive, and I hope you're all doing just as good or better than me. Okay. Anyways, today I'm going to be covering a couple subjects. One of them is some issues were raised and questions, or some comments were made. I want to address those comments. And incidentally, just want to remind people I do not answer comments in YouTube. I do not answer them in Quora. I do not answer them in Facebook. I channel everyone through Patreon. Okay. And Patreon, you do not have to make a donation or contribute anything. All you have to do is be, register and have an account. That's it. Okay, so you do not need to pay anything to get into Patreon and leave a question. But that doesn't mean that I do not address people who do put comments in YouTube. And if the comments are interesting, yeah, sure, I'll address them. And that's what I'm going to do here today. And that's one of the issues. The other one, if I can get to it, hopefully, I'll talk about the principle of equivalence, okay? Okay, so let's get on with it. One individual put this comment, and he says, see if I can make it a little bigger for me. Static objects are actually concepts, principles, since an object, matter, quotation, parenthesis, is always changing from one form to another. They are exclusively manifested or visualized through time. Too many problems with all those, and I've underlined the issues I want to address. The first one is this one. We define an object as that which has shape, and there you see some of the synonyms. And on the other hand, a concept is a word that invokes two objects or embodies two objects or two words that are treated as objects. Okay, so a concept is different than an object. And it's up to people to define these terms if they're going to use them. If someone thinks that an object is a concept, just a concept, like you say, a square, is that an object? Well, according to this definition here, it is because it has shape. So someone says, well, but a square is a concept. Okay, and again, people introduce definitions or notions of ordinary speech indiscriminately into science, into the scientific environment. So if you do that, then we're going to ask you to define the word concept very rigorously, okay? And there you have it. That's the definition of concept. How about matter? Is an object the same thing as matter? Well, not really. We define an object as that which has shape. Again, those synonyms there. We define these terms: distance, which is the separation between two objects; location, which is the set of all the distances from one object to all the others in the universe. Okay, that's location. And then we have exist, or existence, which is physical presence, an object plus location. An object must have location in the universe with respect to all other matter if it wants to exist. This means that if we take the distances from one object to all the others in the universe, and we take that set of distances, that's the physical location of the object in the universe, even if you're talking about a single atom. And matter is the set of objects that exist. Okay, so an object is that which has shape, and matter is a set of objects that exist. And matter is not equal or synonymous with object. Okay, how about the changing and visualized? Well, we discussed that last time, so I'll go briefly through it. Object, that which has shape; distance, again, separation between two objects; location, the set of distances. And what is motion? Motion is two or more locations of an object. Okay, so an object is, you have to define the word object before you define anything related to motion. For example, the word changing or the word visualized. Visualized also requires a second object. Someone has to do the visualizing. Someone has to do the touching. And that's why no verb can be included as a criterion for the definition of object. Okay, someone else mentioned, well, let me just go through this first here. We have, give me a second here. Here we have a blob, okay, and it's moving. Well, you say, well, what is the shape of the blob? I can't imagine what shape it has. The question is not what is the shape of energy, what is the shape of mass, what is the shape of a blob. The question is, does it have shape? That's a yes or no type of question. Water has shape. Gas, any gas, has shape. It's whatever shape you want to give it. You can mold it into anything you want. Air, atmosphere, covers the earth as a shell. That's the shape of air that covers the earth. If an astronaut takes a balloon out into space, I showed that last time, he pops the balloon and he's got some gas in it. That blob, which could be look like something like this one, floats in space. That blob has shape, has finite size. Okay, whatever. It occupies a certain volume, and that blob, you may not be able to describe what the shape of it is. We don't care. Does it have shape? And that's a yes or no type of question. So again, so here's the blob. If you want to, that's how you do it. You just take a snapshot of it. There you have the snapshot of the blob. Does it have shape? Yes. The answer is yes. Okay, so a blob does have shape, and that could be air, that could be water, that could be anything. Okay, it doesn't matter. Okay, another fellow asked a question regarding exist. Okay, let's see if I can get this. Well, first there was another fellow also who asked this question. Objects similar to matter being measure of resistance to a force. Again, an object is not matter, an object is not resistance, and an object has nothing to do with force. And we do not test an object to make sure that it's an object. In other words, we do not check to see if it has resistance to flow before we call a star or a chair an object. A star and a chair are objects anywhere in the universe because the word star, the word chair refers always to an object. Okay? It's something that has shape. Okay, but anyway, someone raised the issue of existence. Okay, and see if I can find it. Here it is. And he says, in my religion, God is an object with location. So how has my religion died, sir? Okay, very good question. I think it needs to be addressed. Okay. And how do we address it? Well, the first thing, well, there's several issues that are raised in that same question. Okay. And so let's go with the first one. The first one is, if we're going to use the word religion, we have to define it scientifically. And this is the way we define it. Okay. We say that science is physical interpretations. It's an explanation, a rational explanation. Religion, on the other hand, has irrational explanations, beliefs, opinions. So there's a difference between religion and science, and the difference is not God. God has nothing to do with it. That's in ordinary speech. Everybody relates religion to God. But see, not all religions have gods. General relativity is a religion. Quantum mechanics is a religion. Mathematical physics is in its entirety. Its physical interpretations are all irrational. They use terms such as space-time. They bring ideas or theories such as Big Bang. They bring terms such as black hole. Okay, and so all these terms, none of them relate to God. They have nothing to do with the word God, at least the traditional notion of God, the one of the Old Testament or even of the New Testament, where God is related to the word spirit. John says, God is love, God is spirit. Okay, so the one that's used in general relativity is not a God. And still, it's religion. Why is it religion? Because it has an irrational explanation. That's why for physical phenomena. And so we have to somehow encompass general relativity or irrational explanations within the definition of religion. So So in order to define the word religion, we can't just relate it to God. Religion means opinion. That's what religion means. Anyone who has an opinion has a religion. Anyone who has a belief has any religion. Has nothing to do with science. Science is about explaining theories, okay? Explaining a phenomenon. So explanations are not the same thing as opinions and beliefs, especially if they are irrational beliefs or irrational theories and irrational explanations. So, first we define the word religion, and therefore this gentleman's, let me put that back up here again, put myself so I don't lose myself, okay? So that he says, in my religion, God is an object with locations. How has my religion died? Well, religion again, it has nothing to do with God. Okay, so it's not a question of whether God exists or not. A question of religion. The question of religion is: do you have a rational explanation first? And second, yes, you have all these proposals, such as God, in which God is presented just like space time, no difference, where they're presented as physical objects here and as abstract concepts over there. And it's up to the theorist to determine or to tell the crowd, to tell the audience, is your God this guy with hands that moves a magic wand and makes the universe? Or is God it could be also the burning bush, right, in Moses, right? Or is God an abstract concept? Is God love? Is God intelligence? Is God spirit? You know, those are, so God can't be both. Either God is, a human-like figure that made us in His image, for example, or God is a concept. And that's the problem we have also in general relativity and quantum mechanics, where they turn, concepts into objects. Okay, and so that's the first issue. The second issue is he says that his God has is an object. It has location, and therefore, according to the definition, the scientific definition of exist, God exists. And he is totally right. Yeah, no challenge there whatsoever. So let me put this up here if I can find it. Here it is. So here's the summary: religion, belief, opinion, proof, knowledge, irrational explanations. All that is religion. Anyone who talks about proof, about knowledge, they're talking about religion, among other reasons, because the word knowledge is defined in terms of belief. They're still using Plato's justified true belief as a definition for knowledge. But even all the alternatives, we have no definition of the word knowledge today, so it doesn't matter. Knowledge is belief. That's what it is. You have knowledge is to you. You know that God exists. Well, I don't, or your neighbor doesn't. Okay. And physics deals with rational explanations of causes and mechanisms. Philosophy deals with rational explanations of purposes and reasons. Okay, you might say, well, what is rational to you is irrational to me. Well, no, we have criteria for that as well. And so we have here a quick rundown. I'm not going to go through all the details. I've done that in other videos. But converting a concept into a physical object, then pretend to move the concept around and saying, I'm moving an object. You move the heart around, you're saying, well, the heart is love, and I'm moving love. No, you're moving a heart, you're not moving love. And that's the big problem in mathematical physics. They say they move energy, they transfer energy, they move a mass, they bend time, they carry a force. They have all these terms which are all irrational. And then you also have the issue of using undefined terms or using them inconsistently. Theory doesn't follow from the assumptions, and also to say that you describe when you that you explain when you actually described, especially mathematically. Okay, does God exist? Well, according to this gentleman. Well, if he says that God has location and God is an object, then yeah, he exists by definition. Okay? Remember, we don't have a theory of God. There can't be a theory of a table. You can't have, I have a theory of a table. No, no, you don't have a, table is a proposal. It's an assumption. And here God is an assumption as well. You say, let us assume that God exists. See, that's different than what the atheists say, what the theists say, and what the agnostics say. All these people talk about the existence of God in terms of belief, knowledge, and they say, well, how do I know that God exists? Can I prove whether God exists? Is there an experiment I can run? None of that has anything to do with science. In science, we say, let us assume that God exists. What do we mean by that? We mean that God is a physical object, in this case, a human like figure, and that God has location, has distance from all the objects in the universe. Okay, so now God exists by definition. Okay, and again, that doesn't have anything to do with religion. It has to do with presenting your hypothesis before you tell your theory. Now you can move on to your theory and say, well, God created the universe. Okay, tell me the mechanism. That's what I want to know. I want to know the mechanism. Okay, because that's what physics is about. That's what science tries to figure out, explanations. Okay, you go into quantum mechanics, they do it in a different way. They say, oh, there's a particle. The particle exists. And you say, well, what is a particle? Well, a particle is really a vibrating field, and they show something similar to this, okay? And you say, oh, that's a particle? And yeah, it's a field that is vibrating. And all you have, all these little particles out there, and they're all vibrating fields. They're local vibrations of the field. It's like a knot. That's the idea they want to give you. And you say, well, what's that field? What's that spider's web? And that's what they've never defined, because when you look up the word field, it's just a bunch of values, magnitudes around an object. Whether you're talking about gravitational field, magnetic field, or whatever, they're talking about numbers, what the value is around the center of magnetism, the center of gravity, or electricity, or whatever. Okay, and another way they present the particle also is, they say that energy, that particle is just a bunch of energy. And here you have a positive and a virtual particle, and these particles, how do they come into being? Well, you start with energy, okay, something that looks like this, which they never defined, but you have to imagine it like some smoke out there, and then these particles somehow materialize and turn into particles. Okay, that's in the religion of quantum mechanics. They magically say, well, it's just a bunch of vibrating fields or energy which somehow materialized. Okay. Okay, so that gives you an idea where the word object stands. An object is that which has shape. It's not that which we can touch, and it's not that which we can move. It's not that which we can see, and it's not that which equal to matter. Matter is a different thing. Matter is the set of all objects that exist. Okay. Okay, let's move on to the principle of equivalence, which is what I wanted to talk about today, and which I left off the other day. Okay, so here we have, this was the version that the the mainstream has, which is Brian Greene in his, what was it, The Elegant Universe. He presents a case where he says, look, if you have the sun disappear, right? Gravity doesn't disappear instantaneously, and the reason it cannot disappear instantaneously is because nothing can travel faster than light. So they're assuming that gravity is something that travels. Okay, they're thinking that gravity is something that travels from the sun to the earth constantly, and it can't do so faster than light, so gravity cannot travel faster than light. That's the logic. And this is how they illustrate it. Okay, you can see that, give me a second here, the sun disappears, okay, and all the planets, according to Newton, fly out instantaneously. But according to general relativity, it takes at least 8 minutes for you to receive the message that the sun has disappeared. You would still be receiving light, you would still be receiving gravity until 8 minutes later, which is the velocity of light. Well, the dissidents do not agree with this completely. In fact, they don't agree with it at all. Well, let me show you another aspect of this. This is essentially what they're saying. They're saying is, if you cut a rope, tightrope walker, right? Um, the guy won't fall instantaneously until the signal reaches him, until the information reaches his feet. Okay, that's essentially what these people are saying. They're saying that the mountaineer that, if you cut the rope, the guy below him who's hanging from that rope, he won't fall instantaneously. It'll take time for the information to reach him that the rope has been cut. So that's the notion that general relativity puts out there. Okay. And well, okay, the dissidents do not agree completely here. As I presented it last week, I'll just run down real quick through this. According to the electric universe, these people say gravity does not involve time, and they're correct. Because if you look at Newton's law, which is gravitational law, which is on the lower left-hand corner in red, force equals gravitational constant g, mass 1, mass 2 over distance squared. So that distance squared is just separation between the two masses. That's essentially what Newton was proposing. And so it does not involve time. It just involves distance. Okay. But then the same electric universe kind of contradicts itself. It says gravity must act instantly. Yeah, whatever instantly means, right? But then they say it travels at near infinite speed. And you have a fellow, his name Tom von Flandern, who wrote a paper, and it's online. You can look it up. He said he calculated the speed of gravity to be 2 times 10 to the 10th c. In other words, it's almost, you could say, infinite. It's close. It's many times faster than the velocity of light. And with this, he's saying that there is something that travels faster than light, which is gravity. And that's essentially what Ralph Sansbury, the guy who came up with all this for the electric universe, says as well. That they say that it acts pretty much at near infinite speed, whatever that means. Okay. And what was the problem with this? Well, the first problem I had with this is that, we have weight. Okay. And according to Newton's equation, if you take one step closer to the sun, your weight changes instantaneously. It changes instantaneously, and we're just going to use that word loosely, because the distance between you and the sun has changed. So all you got to take is one step towards the sun, and you changed your weight, or one step farther away from the earth or closer to the earth, and your weight changes instantaneously. Now, um, how can you do this with particles? Like here's the issue with particles. What if the sun were to throw particles at the Earth? Well, you cannot imagine this being instantaneously. You would have to think of it in terms of what Brian Greene showed or illustrated, which is, that it takes time. And it would take, in the official version, it takes 8 minutes. Okay, so we cannot imagine this being mediated, gravity being mediated by particles. Okay, so that's the issue. Weight changes instantaneously. There you have it. You take just one step towards the earth, one step towards the sun, towards whatever, towards the moon. Your weight should change instantaneously. Okay? And the first problem, as I explained last week, is the problem with the word instantaneous. We cannot use it really in physics. Motion cannot be instantaneous because motion involves, according to the definition of motion, 2 or more locations. It involves 2 frames of the movie, 2 frames of the universal movie. You need at least 2 frames. And so instantly has to be taken only in the sense of moving from one frame to the next. If you call that instantly, well, fine, then use the word instant. But the point is that the only way you can imagine this is in 2 frames or more. And certainly you cannot imagine anything in 2 frames or more with particles, especially when you need lots of frames. Yeah, you would need 8 minutes, and then you would have to do with particles. And particles cannot simulate Newton's equation. And that was the problem Newton had. Newton was thinking in terms of particles. He was a particle man, a corpuscle man. And what he said is, He was thinking in terms of particles because he was thinking of light. And then he says, okay, here's the notion for gravity. We have mass times mass divided by distance squared. Okay, and what does that mean? Well, he said, I have no hypothesis. I cannot explain it because he was thinking in terms of particles and he could not imagine the sun throwing particles at the earth or the earth at the moon and causing this attraction somehow. So he could not imagine the mechanism, especially one that is free of time, devoid of time. It has to be only distance. And if the moon came a little closer to the earth, the weight of the moon would change, compared to the earth. Or if you move closer to the earth, if you're an astronaut, you're coming closer and closer to the earth, your weight changes. Your weight changes for every location that you have. So if we freeze your image, okay, I'm going to go into this next, but if we freeze your image at that point, you have a certain weight, okay? That's frame one. Now you move one step closer. We'll call that frame two. Frame two has a different weight than frame one. How did you achieve that with particles going back and forth? Instantaneously, quotation, right? That's the issue. That's the issue before us. And yeah, with the rope, you can immediately explain Newton's equation very easily. You have an elephant, which has 8 electromagnetic ropes tied to 8 atoms, really 24 atoms, but every set of 3, you'll see the colors blue, green, and red. I hope you can see the little atoms there on the elephant. Okay, there's a couple of them in the trunk, in his body, and his tail. Okay, and they're all superimposed. The ropes are on the same axis, so they pull as one. And I'll use that word pull very liberally. It's really a tension, but I went over that last week, and I might go over it in the future. But essentially, they're on the same axis. When the elephant moves closer to the earth, now the ropes start fanning out. You can see now we have 24 ropes coming out timidly from atoms which are no longer aligned. That's how you produce instantaneity. And you can see, even in this case, it takes 2 frames. So what you have to keep in mind is the word instantaneous should be used in the context of 2 frames, from one frame to another. If you want to call that instantaneous, okay, fine. But that's the context. The context is that from one universal frame to the next universal frame, the number of ropes changes if the distance between the 2 objects change. Okay, so we can explain this very easily with a rope model. You cannot explain it with the particle model. Okay, so that's the issue. That's the starting point. But we still haven't explained the principle of equivalence. And so let's see if we can get into that. We have an astronaut, okay, and he's falling to Earth. We're going to assume that he's falling free fall, so he falls at a rate of 9.8 meters per second squared. That's the acceleration, okay? So he's accelerating towards Earth at that acceleration, okay? He's accelerating every second. He's accelerating 9.8 meters per second, okay, for every second that goes by. That's the speed. In other words, his speed is increasing as he approaches the Earth. That's the point, okay? And that's free fall. How is that equal to a rocket that's in the middle of space and is just pushing, against nothing, against its own inertia? In other words, it has these boosters, and as soon as it presses the button and the boost, the flames or whatever go out its butt, the rocket moves forward. And you say, well, what is the context? Why would these two, gravitational mass and inertial mass, be equal? Why would they, if the rocket accelerates at g at 9.8 meters per second squared, why would they be equal? Okay, this is what Einstein tried to figure out. He had a problem with that. Now he put it as a principle. That's what's called the principle of equivalence, but it doesn't mean he had an explanation for it. Okay, so let's see if I can get this. Give me a second here. So I prepared the little GIF. Okay. You'll see why that's the case. We're going to see the little elephant that I've got, and he's going to be falling to Earth. He's our astronaut. Okay, and here it goes. Okay, we have an elephant falling to Earth. Okay, and what's happening to this elephant? Well, I'm saying that every atom in his body is tied with electromagnetic ropes to every atom on Earth. So when he's far away, the ropes come together, and when he's closer, they fan out. That's essentially the theory. Okay, and as you can see, as he falls to the Earth, the ropes are no longer aligned on the same axis as he falls down to the Earth. Okay. Okay, so let's go with the first scenario. The first scenario is that the one that I just explained. You have here, this is just the gravitational G, the 9.8 meters per second square, just a free fall to Earth. Okay, so the elephant has a certain number of ropes at that distance. Okay, every atom, now here I only show one couple ropes. Okay, you have to think of the elephant being bound by every atom in his body is tied to every atom on Earth. Okay, so they're all pulling. The farther away he is, the ropes fall on the same axis. The closer the elephant is to Earth, the more the ropes fan out. Okay, that's going to be the mechanism that I'm going to explain for acceleration of gravity. Okay, but it turns out that if the elephant flies out in the opposite direction, like from Earth outwards into space, he's got the same number of ropes tied to him at that same distance. Okay? So at the same distance to Earth, whether the elephant comes towards the Earth or the elephant is getting away from the Earth, okay? It doesn't really matter. Here I have them both in one, okay? It doesn't really matter because the elephant has the same number of ropes at a given distance. His weight will be the same at that distance, okay? And the weight is determined by the number of independent ropes that act upon the elephant at a given distance from the Earth. Okay, we still haven't explained the principle of equivalence. All I'm saying here is that at a certain distance, you've got a certain number of ropes, okay? And here's a graphic representation of the problem. Okay, we have this fellow who's in a rocket, okay, and he's gonna get the rocket to move, and the ball will fall down to the floor while he's in the rocket. So there's something bringing the ball down, and he's also being pulled towards the floor as the rocket accelerates. Okay, and he's not even close to Earth. This could happen in the middle of space, no, in the middle between the Earth and the Moon, for example, right? So if the rocket accelerates, okay, both him and the ball get flattened towards the floor of the spacecraft. And that's pretty much what we see with the guy on Earth. If we have the same acceleration, okay, 9.8 meters per second square. If you let go of the ball falls at that speed, at that acceleration, right, towards the center of the Earth. So Einstein was asking, how are these two the same? When one is gravitation, which is the one on the right, and the other one it's just an acceleration. And the one on the left really is Newton's force equals mass times acceleration. The one on the right is the gravitational law, which is force equals the gravitational constant, mass divided by distance squared. So these two, if they have the same value, the question is, what is the difference between them? Is there a physical interpretation for this? Why, when the rocket accelerates, why would the ball fall towards the floor? Why would the guy be suddenly, his feet or his whole body being drawn to the floor as the rocket accelerates? And the answer comes from Mach's principle, okay? Here we have, let's see if I can get this up here. Okay, here we have, again, the situation where the astronaut falls towards the Earth, and we have a rocket that is just accelerating in the middle of space. There is no Earth there to pull it or to push it. There's nothing there acting upon the rocket. And so the question is, what is the physical reason for this? And again, it's the Mach's principle, and that means that every atom of the rocket is tied to every atom in the universe before it even moves. So if you have a certain speed, suddenly you turn your boosters on, you start accelerating faster, you're tugging against every atom in the universe, because every atom in the universe is connected to every atom in that rocket, including you, including the astronaut. Okay, so it's no different. The situation is really no different than the astronaut falling to Earth. That astronaut, by the way, is being pulled by every atom in the universe as well. The reason he falls to Earth is because that's the nearest object, and that's the one that has the greatest influence because of distance. Remember, it's mass divided by distance squared. In the case of the rocket, it's just pure Mach's principle. Okay, and Mach's principle means that, well, I'll illustrate it here in a second here. Okay, here you've probably seen this somewhere. You see the dancer, and she twirls around. And the question is, she opens up her arms and she twirls. And the question is, what is she twirling with respect to? What is it that when you turn around, you feel the force of your arms being pulled outwards. What's pulling on you? When you turn around. And the answer is that you're being pulled by every star in the universe. They're far away, so the distance squared issue comes into play here. But that's what you're pulling against. You're pulling against the ropes of your body, of your every atom in your body, tied to every atom in the universe. Okay, that's what you're pulling against, and that's why the rocket also every atom of the rocket is tied to every atom in the universe. That's why when you turn on the boosters, you get shoved to the back of the craft. You get pushed towards your seat. You're essentially being pulled by every atom in the universe. And there's a famous experiment designed by Newton. It's called Newton's bucket, and it looks something like that. It says that when if you hold a bucket and you put water in it, and the more you twirl, you can do this at home, by the way. If you twirl the bucket, you'll see that the water level starts forming this concave surface, and the water tends to rush towards the edges. And again, this is like the skater. What is it that pulls those drops of water in that direction? Why does it pull on the edges upwards and in the center downwards? Why does the level of the water become unlevel and suddenly form that concave pattern? And again, the answer is that the bucket, every drop of water in there is pulling against every atom in the universe. That's what it is. That's known as Mach's principle. Mach's principle, not Mark's principle. So that's Mach's principle. It means that somehow we're connected to the universe. And the only way you can explain connection, instantaneous connection, is if every atom in the universe is interconnected. Okay? And so that gives you an idea of at least the rope model, of how the rope model explains Mach's principle, which it explains to you in a graphic way, in a pictorial way, why we when you twirl around, your arms come outwards, and you see those skaters, they start twirling their arms around and they kind of close in on themselves and they keep twirling. Well, they're being pulled by something, and that's something we have to identify. And you can't do it with particles, for sure. So this deal about using ether. Ether is just a bunch of particles. Lots of people love to use the ether because that's what we've had for 10,000 years. In fact, nothing changed since the days of the Greeks. We're still using particles in quantum mechanics. We're using the particle model for general relativity, and string theory also uses the particle model because according to string theory, a particle is a vibrating string, and a string is made out of particles, and so on. It's a circular reasoning. Now, with a rope model, it's very easy. Every atom is interconnected. Okay? And of course, people say, well, Bill, how come we can't see these ropes? How come we can walk across them? Wouldn't they tangle and make a big, tied into knots? Well, Mother Nature was smart. Okay? She was smart because, by the way, the same problem occurs with particles. If particles are going everywhere, they should all be bouncing. But people don't ask that question. They think they ask the rope because that's the first thing that comes to their mind. They say, well don't these ropes tangle? Well, don't the particles hit? Did you ever ask that question? Don't the gravity particles from one planet to another interfere with the particles coming from another planet, from Jupiter to the sun, and so on? Nobody asks these questions for the particle model. And no, Mother Nature in her wise ways, or Father Universe, or God, or Zeus, someone out there, I guess, they made sure that all these things were invisible and untouchable. And people say, well, Bill, you're kind of accommodating your theory there. Well, nobody asks, again, what does the rope smell like? What does the rope taste like? What sound does the rope make when it vibrates? Can we go test it in the lab? Nobody asks these questions. They only worry about touch and see because that's the first thing that comes to their minds, touch and see. And that's why the definition you'll find in ordinary dictionaries for the word object is touch and see. And no, the definition is shape. The criterion for the word object is shape. Not all objects can be touched, not all objects can be seen. All objects had shape. Okay? So the rope has shape. The rope cannot be touched. The rope cannot be seen. You cannot go to the lab and say, well, let me run an experiment to see if the rope exists. No such thing. Well, there is one experiment I designed, and I call it the slit in a vac. Some people are aware of it. It's got to do with, and you don't really need the slit. What you have is you have a chamber, okay, and you put a laser pointer, and you pointed it at something, at a sensor. For example, photosensitometer. Okay, photosensitometer can tell you a little bit about the intensity of light. Okay, so you have a certain intensity. Okay, so you have a laser pointing at this photo multiplier, and it gives you a certain intensity. It counts essentially the number of blips it receives. Okay, so it's a little biased towards quantum mechanics, but we can forget about that to some degree. You have the laser pointing. You have a certain intensity. You put the whole assembly in a vacuum chamber. Okay, now you pump the chamber down. You pump it down, gradually. Put your mechanical pumps, your diffusion pumps, or cryo pumps, whatever. You pump it down. You can pump it down to 10 to the minus 3 torr level, minus 5, minus 6, minus 7. You're removing garbage from the chamber. Okay, you're removing atoms from the chamber. Well, if light, gravity also, consists of particles, well, the mean free path is now greater. Now light has nothing to bounce against. The particles of light, the photons, they have nothing to bounce against because you're removing stuff from the chamber. You're removing atoms. If you had perfect vacuum, light should, all these balls, these photon balls, they have nothing to bounce against. You should get the highest intensity possible. And the more garbage you put in there, like if you fill the chamber back again to atmospheric pressure, now you have a lot of garbage in there. Now light, the photons hit against all these particles that are in its way, and now the intensity should drop. So let's get that right. The particle model, anyone proposing particles in any way, shape, or form has a problem because they're saying that if we put this in a chamber, in a vacuum chamber, right, and we pump the chamber down, the mean free path increases, and you should get a higher intensity at your photosensitometer. And I'm saying that's nonsense. It's absolute nonsense. It's not going to happen. Okay, what you're going to get is you're going to get the same or lower. And that's because when you remove atoms from the chamber, okay, light goes from atom to atom. The rope is connected from atom to atom. If you remove atoms, okay, your intensity should drop because now you don't have enough atoms to relay the signal towards the photosensitometer. It either should drop or stay the same because it would be very hard to measure the distance in a small vacuum chamber. When you remove one atom, the distance there is so small that you may not notice it. But for sure, it's not going to increase like quantum would predict. Okay, and here we have another situation, also having to do with the principle of equivalence. And this comes out of Einstein, and he says, if you take, let's see if I can get this thing up here. Okay, you've got this situation where you're in a rocket, okay? And according to Einstein, light bends. That's what he says, okay? He says if the rocket goes up, if it's standing still, the light will go straight. But if you accelerate the rocket, okay, you put a little fire underneath and get that rocket moving, now he says the light will bend. Okay, that's what he says. Well, I don't know. I got a problem with Einstein's conclusions here. Let's take his laser, okay, and let's put it in a desert, okay. And I'm gonna have this laser pointed at a mirror, and we're gonna get the longest distance we can get out there in the desert. We really want a long distance, okay? We want to test this real good. So you can point the laser at a mirror out there, okay? And what happens? Let me get this thing in here. Give me a second here. Okay, what happens? Well, if um, if you point the laser at whatever, you can point it at a mirror, right? But it's better to point it at a single spot, okay? A little spot. If you can pinpoint it, that would be great because that's what we're going to test. We're going to test whether gravity deviates the beam. Okay, that's what we're going to test. So how are we going to test it? Well, let's put a bunch of trucks there. Okay, we're going to line a gazillion trucks filled with all kind of garbage. Okay, on one side of the laser. Will the laser point to the same spot, or will it be deviated by the gravity that you have from the trucks? Because if gravity bends light, well, here's a good place to test it. You just point a laser at a mirror, and then you put a bunch of trucks to the side. Before and after, there should be a change. And I'm saying the trucks won't affect the beam at all. And this is the question that I've got. That Einstein reached a wrong conclusion. In fact, you'll notice that you can do this test at home. Okay, also in the presence of a trained relativist. Okay, you can run a laser through a magnet, through two magnets, and you will see that the magnetic field also will not deviate your beam. Neither will a magnetic field, nor will gravity change the beam of light. Why? Because light is mediated by a rope that connects two atoms. Rope is always straight. It's pulled tight. So in that sense, it's straight. It's an undulating configuration, but for our purposes, it travels straight always. And that's why, there's another experiment that kind of shows this, and it's known as ray reversibility. And that's if you shine a laser or light, any light, through a series of mirrors, okay, so that it's fixed and you can see the light going, from one mirror to the other, and you just look at that setup. Well, light travels in both directions, and it travels along the same path. If light curved, I mean, here's the Earth moving, right? Then we shouldn't see it always in the same place. Light should move somehow, deviate, or get bent or whatever. That's not the case. Optics will show you very clearly that if you shine a light through several mirrors, light goes in both directions and it won't deviate. So Einstein is wrong, simply wrong. It just doesn't match reality. Okay, neither does gravity warp light, as he claims. Neither does light ever travel in curves. And some people say, well, Arthur Eddington, 1919, he proof religion. He proved to some people who believe it, right, that light warps around the sun. He took a picture, went with his crew, I think to the Pacific, and what they did, they looked at, there was an eclipse, a star behind the sun. So when the eclipse came, the moon in front of the sun, okay, they could still see the star. And they took a picture of this image from that star that was behind the sun. And they said, we have proof. Light curves around the sun. That's why we were able to take that picture. Well, not true. We have a different explanation here. And let's look at that explanation. An explanation, as always, we do it graphically so that you can understand it. A baby can understand it. You don't need to go to college to understand this. Okay, here we have the same situation. We have the moon blocking the sun. And you can see that the star way out there in the middle of nowhere is shining. In other words, every atom there is connected to every atom that comprises the sun, including the corona of the sun. Okay? And what the corona does is have atoms that are connected to us, to your eye. They're connected to everything on Earth. And so the reason we can see a star that's behind the sun during an eclipse is that the corona is relaying, the atoms of the corona are relaying the signal in straight lines to your eye. We do not need to curve light. We do not need to bend light. All we need to do is do it with straight lines. Okay? So with the rope model, we can explain all these things without getting into, all these sophisticated things where they say light curves. Because if it's true, if Einstein is correct, and light curves in any way, shape, or form around the sun or anyway, well, we got a problem because we have angular momentum. And what that means is that the speed of light changes. But special relativity is founded, and so is general relativity for that matter, founded on the principle that light travels always at the same speed in a given frame of reference. And that can't be if space-time is full of potholes. Every atom in the universe supposedly creates a little depression in space-time. Everything that has weight, everything that has mass, hopefully an atom has mass, creates a little dent. Unmeasurable, that's irrelevant, but it creates a little blip in space-time. And so light would have to go through all these blips, especially if you have big monsters like planets and stars weighing down space-time. That light should curve around everywhere, which is what Einstein is saying. But if that's the case, then light should not be traveling at little c at 300,000 kilometers per second, even out there in space, in a vacuum. Okay? So Einstein has a problem because he's got a contradiction between the principle of the light traveling at always at a constant speed, and general relativity says that that gravity, the warpage of space, changes the speed of light. You have angular momentum. If light travels straight, no problem. But what happens when dips into one of the depressions in space-time? Now you have a different speed of light. Okay. So and one of the problems there is that the mathematicians, they always use little c for everything. They put it in every equation, and they can't do that. They can't do that because according to general relativity, space-time warps. It creates a depression, like the sun, for example. They say light curves, and if light curves, you can't use little c in your equation. Now you got to change the speed of light. And they always put the speed of light. They don't care. So summarizing, the principle of equivalence is essentially, right, that it's really a difference between push and pull. Gravity is pull. If you want to consider pull, it's not really pull, it's drifting. Okay, the object, the asteroid is drifting towards the Earth. As it drifts, the ropes fan out. Okay, if you want to call that pull, we'll call it pull. Fine. But what happens when the rocket leaves the Earth? Now you're talking about push. It's being pushed outwards, not being pulled from the front. It puts its boosters, its rockets, it is pushed upwards. Why do you fall back towards your seat? Why does the astronaut get flattened towards his seat when the rocket goes up? Because he's pulling, here on Earth, he's pulling against the Earth. Okay, that's the nearest object, massive object. But out there in space, he can do the same thing. He can accelerate his rocket. What is he pulling against there? He's pulling, according to Mach's principle, against every star in the universe. Every atom of his body, every atom of that rocket is tied to every atom in the universe. Now this guy accelerates against that, and he's being pulled by every rope tied to his body. That's what it is. Why don't they pull him right through the seat? Because of mass, because of distance squared. The distances are so far away that they affect him very little, but it's still physically he's tied to every atom in the universe. It's like a spider tied to a spider web, or something like that. Okay. Okay. With that, I'll see you next time. I'll see you on Wednesday, and we'll see you then. Hopefully, you'll be in better health than I am by then. We'll see you then. Bye bye.